Okay, so let's unpack this.
Let's do it.
We're doing a deep dive into the real blueprints for quantum teleportation. We've got sources here packed with the physics, the advanced math protocols.
Yeah, the heavy stuff.
Exactly. And our mission really is to just cut through that density and pull out the core building blocks. You know, what actually lets you transfer quantum information without a physical connection.
You have to start with the biggest shift from, classical computing.
The bit versus the qubit.
Right. A classical bit
Yeah.
it's simple. It's a 0 or a 1. It's a definite state. You can measure it a million times, and it's still a 0 or a 1.
But the qubit, that's a whole different game. All that certainty just vanishes.
It does. A qubit exists in what we call a superposition of its states,
Mm.
both at 0 angle and area 1 angle at the same time, in a way.
And when you measure it.
The outcome is probabilistic. You get a 0 or a 1, and the very act of measuring it forces the choice. It collapses the state.
So you've generally destroyed the information you were trying to read.
You have. And to even describe this mathematically, you can't use normal geometry. You need the linear algebra of Hilbert space. It's a much bigger, more complex world.
Okay, so that's our information carrier. This delicate, probabilistic qubit. What's the fuel? What actually drives the teleportation?
It's all about entanglement.
Yeah.
100%. It's this non-local quantum correlation. That's your channel.
It creates this instantaneous link.
Exactly. And the sources that define it by its inseparability.
Right, I saw that. So if you have two systems, A and B, their combined state can't be factored. You can't just write it as state A times state B.
You can't. And that's not just the math trick. That's the physics. It means you literally can't treat them as two independent things anymore, no matter how far apart they are.
They share a single identity.
They do.
Right.
And the sources point to specific examples like the Bell states for 2 qubits, or for more complex systems, the GHZ states. These are like high-octane fuel for these communication schemes.
But we have to be really clear on one point for everyone listening, right? This isn't faster than light signaling.
Absolutely not. That's a common misconception. To actually complete the teleportation, to reconstruct the state on the other end, you still have to send information over a classical channel.
Like a phone call or an email saying, okay, here's what measurement I got. Now you can fix your qubit.
Pretty much, yeah. So once you have that entangled link, the protocols get really complex. We're talking multi-qubit, bidirectional, even multi-hop teleportation.
That multi-hop idea is interesting. It implies the channel degrades. You can't just send it across the country in one shot.
You can't. And what's really fascinating here is that every communication system, quantum or not, has to deal with noise. It's unavoidable.
And in the quantum world, that noise attacks the entanglement itself.
It does. It just chews away at that delicate link. Yeah. The sources actually focus on 4 main types of this quantum noise.
What are they?
There's amplitude damping, which is like the state losing energy.
Yeah.
Then bit flip and phase flip, which are pretty self-explanatory.
Well, they flip the state.
Right. And then phase damping, which is about losing the coherence, the quantumness of the state.
So with all this stuff trying to break the connection, how on earth do you know if it even worked?
Well, the key metric for success is called fidelity.
Okay.
It's a calculation. It basically measures how close the qubit you received is to the original one you tried to send. High fidelity is the goal.
And getting high fidelity means you need strategies to fight that noise.
Oh, absolutely. The papers get into weak and reversal measurements, and one of the really advanced ones is called environment-assisted measurement, or EAM.
Environment assisted. So you're using the thing that's causing the problem, the environment, to help you fix it.
In a way, yes. It's about using controlled interactions with the environment to sort of filter out the bad noise, getting you closer to that perfect, ideal transfer.
So what does this all mean for you? It seems like quantum teleportation isn't sci-fi magic. It's this really rigorous engineering challenge built on, 3 pillars?
I think so.
You've got the qubit, this probabilistic bit of information. You've got entanglement, the non-separable resource that fuels it all. And then you have the constant real-world battle against channel noise.
That's a great summary. And that battle brings up a pretty deep final thought.
Lord.
So, in theory, the evolution of a perfectly closed quantum system is, it's unitary. That means it's completely reversible. You can run the clock backwards.
Okay, in a perfect world.
Right. But we just established that any real-world teleportation process will inevitably have non-unitary noise introduced.
Yeah.
So it raises the question, does the practical applied goal of maintaining high fidelity imply that perfect reversibility, that theoretical ideal, is actually impossible in any real quantum communication system we could ever build?